Up and running again. Make sure we can see the board. All right, so I'm going to look at the quotient rule from geometric and numerical perspectives. A lot of approximations. Going to do a lot of approximations with a little bit of help from the calculator. Definitely with the decimals that were generated with this. I went to the calculator. And I'm going to create a quotient here. Sin x divided by x from a product. And so I think that if you haven't looked at the product rule video, I think you probably need to before looking at this one, right? Because I set the stage for how the products work, derivatives of products, geometrically and numerically with much easier functions. And so I encourage you to look at that, but certainly dive in if you want. So working from the product, length times width equals area, dividing by the width, gets us our length equals our area divided by our width. But that could have been expressed as area times 1 over W. And so I picked a couple of functions. I picked one factor of creating this length as the sine function, and the other is 1 over x. And if you multiply these, you get sine x over x, which is a quotient. And so the question is, we could take the product rule, the derivative using the product rule or the quotient rule, but I think it would be easier jumping right to the quotient rule. And hence, it's something that we use. All right, and I picked, well, I should say a little bit about the product rule. The rate at which the rectangular area accumulates is determined by its, and by its I mean the rectangular area, the dimensions of the rectangle, and how those dimensions change. Okay. And I like to use the number 3, and I did it in the product rule as well. Guess you can still see this. If I had a really big circle with a radius of a unit length of 1, doesn't matter the size of the circle, then 360 degrees is really one walk around the circumference of that big circle. And so by picking the value 3 radius lengths, so 3 of these radius lengths would take me here, 3.14 would be halfway around. I think you can see that the sine, using the reference angle over here, using that reference angle, the sine of that, I don't know what it is in degrees. It's got to be near 180, obviously. The sine is this altitude. And as the hand of the clock, think of it as the hand of the clock, rotates, then these altitudes are coming down, whereas the radius lengths are increasing. But if I move this over, pretty hard to see the gap between the two, which means that this altitude and this radius length distance are about the same. So I can get a good approximation here. And for the sine and cosine. So the sine is roughly 0.14 units and the cosine is roughly -1. So that will help us get our first approximation. Did I cover everything there? I think so. So I'll move the camera down here a little bit. All right. And so the jingle for this quotient, where the sine function is our high function, x is our low, kind of numerator denominator. It's a nice little mnemonic. Is low d high minus high d low over low low. And because we're using the number 3, we can get an approximation. I went to the calculator here, but the cosine of 3 is roughly -1, and we're multiplying it by the low 3, right? So 3 times the derivative of sine, which is cosine, 3 times cosine of 3 minus sine of 3 over 3 squared is the quotient rule, and this is an approximation for this quotient. Approximation of its rate of change at 3. And cosine of 3, -1, sine of 3, about 0.14. And I went to the calculator at this stage, and I got -0.3488. All right, so that's just giving you a little bit of a feel for how this area is changing. And it would make sense that it's decreasing because the sine function is going down and the radians are going up. All right, so let's move it up a little bit further to the right here. So looking at, where derivatives come from, it's a slope, right? Rates of change. We're gonna linearize curves by zooming in. Zooming in implies a very small change in X. And up here is kind of our, work with limits. The limit is H goes to 0 of the sine of X plus H minus the sine of X over X plus H minus X. Here's our X plus H minus X. And as H goes to 0, for instance, let H equal 2, we have a jump of 2 units. When X is 1, we're creating 1 unit of change in X. And if we keep doing this, 0.5, I think you get the idea that H is going to 0.1, and I'm using 0.001 as just to get a feel, a numerical feel. Seeing the numbers work is, I think, very important in math. So I want to see the numbers work. So I'm doing some gross approximations. All right, and I'm taking the area of this rectangle when X is 3.001, and I'm going to subtract the area of the rectangle when X is 3, and I'm going to get a feeling for Y2 minus Y1. I'm going to get a feeling for that change, and then I'm going to divide it by the 3 plus 0.01. I think I use 3 decimal places minus 3, and that's 0.0. And I want to work with that. And I went to the calculator for this, especially this one. Wouldn't need to for this. And it's useful to know that when you're dividing by 1 over 1,000, you're going to have to multiply by 1,000 at some point. All right, but when I got that on the calculator, I got minus 0.3455. Okay, and that's compared to this. And they're pretty close. Okay, pretty close. So getting a kind of an organic feel versus using the mnemonic and not worrying about too many decimal place accuracy, I'm in the same ballpark. All right, so we can assume that those calculations have some meaning with respect to what we're talking about. Now, where does it all come from? Well, if you looked at the product rule video, then you'll realize that this side of the rectangle is changing. How does it change? Well, the derivative of sine is cosine. So I'm looking at cosine x dx for that amount of change. And that's going to get multiplied by the fixed x to the minus 1 is the same as 1 over x. And that's going to get me my little change in y, which is really this layering change. I was going to do that in orange, but I'm actually doing 2 layers of change. And actually, it's coming down. I should have actually drawn it on the inside, because we're taking away area here. And, I did some computations with that. So I showed cosine x dx times 1 over x, right, which is the same as that. And I multiplied the derivative of x to the negative 1 is minus 1 times x to the minus 2. And if I multiply that by sine x and use the product rule, I'm adding this product, which means I'm really subtracting sine x over x squared dx to get this change in y. That area of accumulation is actually getting smaller. I hope that makes some sense. And now if I factor dx, I can literally divide it to the other side. And here I have my beginnings of the quotient rule. We need a common denominator, so I got to multiply this side by x over x. And here we are again. X cosine x minus sine x over x squared, which if I substituted 3, would be 3 times cosine of 3, we said was close to negative 1, minus the sine of 3, which is 0.14, close to 0.14, divided by 9. And if I did that on the calculator, coming back over here, I have it somewhere. I guess I gotta do this. I get negative 0.3456. So that's 3 calculations that are in the same ballpark. Okay, and if you broke it up into its significant parts, then cosine x dx turns out to be this number times 1/3, which gets us that. And then we've got cosine of 3 times 0.001 gets me this number here. All right, and if I add those up and divide, if I add those up and I divide by 0.001, it's the same thing as multiplying by 1,000. So I put these together, and it looks like I came out with negative 0.34468. So I did 3 gross approximations, and I think we can see that, you know, we're 3 decimal place accuracy here. So we might be off by a little bit, might be off by a factor of, you know, a little bit around 1,000th or whatever, 3,000ths, 2,000ths, whatever. But we can see that it holds true as to what's going on. The numbers match up with the geometric shapes. And so where does this all come from? I think geometry, the geometry of the figures we're working with. And I think it's important to see that and to contemplate, reflect upon it. And I think you got to do that repetitively in order to see what's going on. And conversations have to start somewhere. So just started a conversation. All right. Okay, I'll post this and let you ponder. Ponder away. I'm going away.